ఆడియో చూడు.
ఇప్పుడు వస్తుంది.
జనరల్ ఆడియో వస్తుంది కదా, నేను మాట్లాడేది వస్తుంది కదా, అది రాకూడదు, అక్కడిది రావాలి మైక్.
నాకు అది కూడా ఇప్పుడు వస్తుంది చూడు, చూడు
నీకు ఒక 20 seconds ఆగొస్తుంది, డిలే ఉంటుంది.
ఫింగర్ వస్తుంది, డిస్టర్బెన్స్ ఆ ఫ్యాన్ వచ్చి ఫ్యాన్ ఏ ఛానల్లో ఉంది ఇప్పుడు?
111 ఇట్లా రావట్లేదు, డిస్టర్బెన్స్ రావట్లేదు. మనం దీన్ని అసలు జనరల్ తీసుకోవద్దు కదా.
Hello, check, hello, check, hello. Voice hello,
Okay.
hello, check, hello. Hello, check. Hello, check, hello. Check my test. Hello. Hello, check my test. Hello, check, hello. Check, hello. Hello, check my testing. Hello. Hello, check.
ఫ్యాన్ ఒకటి బంద్ చేస్తుంది.
ఈ ఫ్యాన్ బంద్ చేయొచ్చు. ఇక పని రిమోట్ ఇక్కడ ఉంది. ఫ్యాన్ ఆఫ్. పని ఇట్లా ఏం మార్చారు ఇక్కడ మళ్ళీ ఏమన్నా మార్చారా?
ఏం మంచి ఆడియో జనరల్ ఆడియో. ఇప్పుడు మాట్లాడండి.
హలో 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 టెస్టింగ్ హలో హలో
ఓకే కదా, ఇది పని చేయట్లేదు, అవసరం లేదు.
హలో చెక్ హలో టెస్టింగ్ హలో హలో చెక్ హలో హలో చెక్ హలో హలో చెక్ హలో This is so okay.
Now go back. Let's continue with the second part of GNSS-R. Sorry.
The pointer. Okay, we can continue. I think I'm going to end a little bit early, I'm not sure, but let's just, actually, let's just pick up where we left off. So I talked about calibration and instruments, and then, remember we introduced the idea of the delayed optic map, which comes from the use of these signals for navigation, their intended use for navigation, the ability to mask the surface in delay and in Doppler. And I talked a little bit about the ambiguity function and the delay Doppler ambiguity. Sorry, got two things mixed up. The delay Doppler ambiguity and the ambiguity function, which describes the signal mapping in delay and Doppler space. So now let's look at how this geometry maps into. Okay, maps into things that are useful for remote sensing, specifically resolution of the ground and coverage. Okay, So remember the delayed Doppler map, we have, contours of constant delay, which approximately form ellipses. If I look at the ideal case with the transmitter at infinity, parallel rays hitting a perfectly flat surface, the solution is an ellipse that's pretty close to what you get from aircraft. So this shows, my ISO range ellipses, constant range from aircraft, and this shows for a spacecraft. And of course, the range for a given point on the ground in a two-dimensional plane, my range will be given by the distance between the transmitter vector, a point on the ground, okay, at position X and Y, and the range from the receiver to that same point on the ground. So I can expand this out, and I can get a nonlinear equation, and I can solve that for my contour of ISO range, maybe not contour, a locus of points for an ISO range area on the ground. Okay, Doppler, we had the Doppler equation a little bit earlier, the dot product between my transmitter velocity and a unit vector going from the transmitter to the point on the ground. I think I had that geometry a little bit earlier here. I probably should have pulled these slides down a little bit earlier, but we have, actually, let's go to this one. Right, well, I have my vector from my transmitter to my point on the ground, unit vector m, and then my point on the ground to my receiver, unit vector n. I have the velocity of the transmitter and the receiver, and you can show that the Doppler to that point on the ground is given by, this dot product minus this dot product. To put it in units of cycles per second, divide by the wavelength. So this one will have units of speed, meters per second, divided by meters per cycle, gives cycle per second for my dot. Okay, so this for a flat surface, transmitter out of infinity, this gives a solution of hyperbola. So the dashed lines are hyperbola. Okay, so those are the two things I want to point out: the geometry, ISO range ellipses, ISO Doppler hyperbola. That's a solution for a flat surface. It's a good approximation for a non-flat surface. The other thing I want to point out is roughly the size of these. So for an aircraft that 4,600 meters, we get the idea that and this is for a GPS CA code. So let's go back to some of the numbers. The CA code is generated at 1.023 megahertz, or approximately 1 megahertz. So if I say, what's the corresponding distance for the time delay of one chip? Okay, so I have 1.023 megahertz, approximately 10 to the 6 cycles per second. Speed of light is 3 times 10 to the 8 meters per second. So if I divide those two, I get the delay of one chip is equivalent to a distance of 300 meters. So that delay of 300 meters on the surface maps into this first ISO range ellipse of about a few kilometers. All right, so that's kind of fundamental resolution if I look at just that one delay. But if we're going to combine multiple measurements and longer delays, our resolution is going to be set by the maximum ISO range ellipse. Okay. Go up the spacecraft, 500 kilometers altitude, and I see now my 3/4 of a chip delay is larger than the 25 kilometer resolution requirement for signals. So we see that the scale of these resolutions based upon my ability to measure points on the delayed operator. Okay. This just shows some of the approximations. I said the formation of an ellipse and hyperbola. If I work on that model for a transmitter way out at infinity, perfectly flat surface, I get the size and shape of the ellipse are given by, this estimator semi-minor axis. If you look at this closely, you'll see that this is basically just a first Fresnel zone, right? If I replace my delay by, the period of just a carrier wave, this will give me the same result for the first Fresnel zone, where my delay is limited by one cycle. So basically, it's the same idea as the Fresnel zone. Okay, so it scales approximately with the square root of altitude and delay. So we go back here, so I go, up about 100 times in altitude, it grows approximately 10 times in size. Okay, so square root of altitude. This maybe is less intuitive, but if I again look at the approximation flat surface, transmitter at infinity, and I look at iso Doppler, constant Doppler, I can, you can see that this amounts to a hyperbola. To me, that's not that obvious, but the points on the ground will provide hyperbola. Okay. Let's see. Okay, so one result of this approximation, if I go back earlier, is this is the size and shape of the area that's illuminated on the surface of the Earth. If I say, well, what are the corresponding delays? Well, for again, our flat Earth solution, it's it's from basic geometry, we get the delay to the specular point as a function of the height and this elevation angle, and this is maybe some of the heritage coming from the navigation world. Remote sensing, everyone likes to use incidence angle, right, which will be, from my surface normal to the incident. The navigation in the world, everyone uses elevation, so this is still in terms of elevation, but you can switch back and forth by just replacing the sine with the cosine. But it's pretty easy to see why I get this result. For the path delay to the specular point is 2 times the height times the sine of the elevation or cosine of incidence angle, and you can kind of just see how this will work, because my point above the surface and altitude of h, if I have my specular reflection, that's equivalent to viewing my signal at some virtual point at h below the surface, and then my parallel rays incident, this additional distance you can show is 2h times sine of the elevation. So okay, that's a way of checking that these results make sense. Okay, and so that's the delay to the specular point, and that's how we can locate the specular points. It's kind of 2 things. One is the size and shape of the area that's observed with a given delay in Doppler around the specular point. The other thing is where is the specular point. And we actually, yesterday, when I was visiting Israel, we actually had some discussions. In some ways, sometimes finding the specular point is not an easy thing to do. Here, I mean, this is the ideal case, perfectly flat surface, right? Everything's clean. Okay. Let's look at how this gets complicated. Well, what if I'm in space? I need to include the fact that I need to start thinking that the Earth is not, a flat surface, right? So if I have a surface of the Earth that's ellipsoidal, finding the location of the specular point on the ellipsoidal Earth becomes a little more complicated. So there's a number of different ways that this can be done. All of them are numerical. And right now, we're assuming that still the Earth is approximated by this ellipsoid. Maybe we could also, look at a higher level gravity field and still apply the same approach. So one thing you can do is specular point is the shortest path delay, right? That I believe Fermat's principle, right? So one thing is an open optimization problem. I can strain my specular point to be somewhere on the surface of this ellipsoid, and I minimize the total path delay. That's what I did early on in this work. I just numerically minimize this, and I can easily replace this surface with something more sophisticated than an ellipse. It's just whatever I use for this model for my position of the surface. Okay. The other thing I can check is that, well, at the local surface, Snell's law has to hold. So I can have this angle, it may be a little hard to see, but this angle of incidence and angle of reflection have to be equal. Another way of saying that is, as we saw before, the normal and the Q vector have to be collinear. So I can come up with various gradient searches to, make those two vectors collinear. I can find setting these two angles equal, or I can use those as tests of another method that may have converged. Okay, so I just list a number of different ways and some references to other papers that have looked at this. Again, this is basically what I did. This may be unconstrained optimization. It's really not unconstrained because in this equation, I'm basically fixing my speculative point to be on the surface. I can kind of explicitly do a constrained optimization by minimizing the path delay with the constraint, and this is kind of a really compact linear algebra way of writing that condition that RS is on the surface of the ellipse. I can also look at minimizing this difference in the Q vector and the local normal. It's called the unit difference gradient. Again, it gets a little more complicated with the ellipsoid order. What gets even more complicated is the fact that we're actually not seeing the reflections from the ellipsoid. We're seeing the geoid. As I said, we can probably go back to that first equation and put in a model for the geoid. The other thing what's done with Cygnus is we actually have, for the ocean surface, we have a mean sea level map that gives the mean sea level minus the ellipsoid, the WGSA4 ellipsoid, that difference. And you just do around the speculative point, just do a gradient search to minimize the path delay or any of these other measurements, the alignment of the N and Q vectors, angle of incidence, angle of reflection, whatever. Okay, from land, it becomes a lot more complicated. The ocean is going to tend to follow the geoid, the gravity field, with some mean sea level measurements. Terrain can be very complicated and very rough. Okay? In fact, the idea of what is a speculative point may not even make sense on land. This is one of the examples that's presented where we actually have a DEM that has two peaks. So if I imagine a rough terrain, like mountains and that, I may get two reflections that are not close to each other, giving me the same delay. So how all this can be untangled, I think, is still a big question. So maybe, so making these measurements very, very extreme terrain, mountains, may raise some questions. Okay. We talked about locating the speculative point. We talked about the mapping the bicycle range and also Doppler lines of the surface, and how that can be used to define a resolution. There's some other things you want to think about resolution, and also in terms of how resolution is related to spatial coverage, because one of the advantages we talk about signals of opportunity is there's many sources out there. The receivers are really simple, or small, not necessarily simple, but small, so we can build them cheaply and put them on small satellites, increasing coverage. Let's talk about how those things are related. Any questions so far? Okay. So we talked about the definition from basically in terms of the maximum delay, but if we're, and again, when I talk about the maximum delay, that is saying if I'm going to assign one measurement to some samples of the delay Doppler map, I may not want to just have the peak, but I may want to compress a number of samples of the delay Doppler map into a single observable. So that says I need to look at the maximum delay, the maximum Doppler, and where those two overlap is going to define my resolution. And so this is from, this one paper, actually, this is a book chapter. I said, well, usually we look at the maximum delay as setting the resolution. But if I narrow my scope and Doppler, I could maybe get some weird resolution shape that looks like that. Okay. And then we're going to say, okay, I'm going to pick a resolution, and I'm going to assign this size of my resolution cell, but it doesn't quite incorporate what is going on with the measurement because the surface is not uniformly weighted. Remember that radar equation, the weighting of the surface comes from the ambiguity function, and that's not uniform. So everything within the given delay and Doppler is going to be weighted based upon the shape of that ambiguity function. So that's one thing. The other thing is, I'm not going to make just one measurement coming out of my delayed Doppler. As with any remote sensing, especially microwave remote sensing, individual measurements are very noisy. So I'm always going to have some amount of average. So if I incorporate a sequence of measurements, I need to account for the fact that I'm moving my specular point over the surface. I'm moving this iso range, iso Doppler, or shape over my surface, and I'm producing a single measurement. So the resolution is going to be dependent upon all these things combined together to look at the total area that goes into that measurement. The other thing is, and this maybe is kind of related to the first one, but similarly, but the specular reflection, closest specular reflection, I may say process a lot of delay units, a lot of delay samples, but all my power is concentrated in only a few near the specular point. All the other ones are just noise, they're not contributing anything. So my specular reflection is going to have a resolution maybe set by the first Fresnel zone given by the comparative frequency, right? So all these things can change this idea of what I'm using for resolution. Okay, so I gave some examples of just some numbers. If I define my resolution of the DDM, so this is assuming I have a diffuse scatter. So this says I'm going to pick a range of delays, range of Dopplers, and assume I have a shape of the DDM within that range of delay and Doppler, right? So some numbers, I think I kind of showed some of these examples before, but if I look at the GPS CA code, 1 megahertz from airborne, I'm looking at a few kilometers. As I go to higher elevations, smaller incidence angles, it gets smaller. That makes sense. As I go to wider band signals, and we haven't said anything about signals of opportunity, so these first two are navigation signals. After Rashmi is going to talk about signals of opportunity, which some of those have very high bandwidth. So if I go to, for comparison, if I go to 400 megahertz, which would be a direct broadcast service, I see, I can get a pretty small resolution by increasing that bandwidth. What the bandwidth tells me is it's going to basically say the space between given delay ellipses, right? So if I set that based on one chip at 1 megahertz, we get about 300 meters. One chip at 10 megahertz, we get about 30 meters. And then 400 megahertz. Let me see if I can do that band in my head. That would be about 1/40th of that. So that would be a few centimeters delay. Okay. Hour, just go out for a minute. Okay, I'll continue as long as the slide is operating. Okay, spacecraft numbers, obviously with the CA code, I'm looking at pretty large resolution cells, so this is going to be comparable to radiometers. The advantage of the wideband for the direct broadcast, and they get down to below a kilometer. Okay, so now if I look at this is diffuse. This is assuming I'm filling up all my delays in my delayed Doppler map, power and all of those. The other thing to look at is averaging, and I said, these both microwave measurements are going to be noisy, so there's going to be some averaging involved. So that's going to decrease my resolution as well. So this just shows an example. This is one of the ISO range of ellipses, like either for one chip or half a chip. And then if I look at my spacecraft moving into its orbit, average 3 of these. In the single measurement, I get some cell that's about the coverage of all these things, which I've approximated as fitting an ellipse to the whole pattern. That's really where my measurement comes from. So I'm kind of weighting two things. I'm weighting a higher accuracy from averaging measurements with the loss of resolution from having spread those measurements out over a larger area. All kinds of other things you can do. You can also, weight these different measurements so that there's more of an effect in the center and stuff like that. Okay, so now I'm going to coherent. Now my resolution is going to be set not by the delay ellipse based upon the cross correlation, but really the presence of that code in the cross correlation is really no longer relevant. Basically, removing all of the bits, or all of the chips, if I line those codes up properly, and I only have this carrier. So having only have the carrier, then the resolution is set by the first Fresnel zone, where here you're going similar square root of the height times the delay. The delay is equal to the wavelength. That's when my signal completely interferes with itself and gets my first null. So now I look at it doesn't depend upon the chipping rate, the code, the navigation signal. It depends just on the carrier. So it doesn't matter what I modulate on this. From airborne, I'm going to get a few hundred meters from L-band. If I go down to these lower frequencies, which Rashmi's going to talk about for signals of opportunity, I get a few hundred meters, a little bit larger. For spacecraft, L-band, first Fresnel zone, I'm going to get in the order of a kilometer resolution. So the results that are presented from Cygnus results for land remote sensing, where they're looking at things like flood inundation and wetlands, where you have very smooth water surfaces, so you get nearly specular reflections. The resolution that they are presenting is on this order, on the order of a kilometer. Okay. Okay, the other thing, this is from a reference to the paper and so on. But of course, there's a relationship between coverage and resolution. So if I'm maybe looking at a requirement to say provide global coverage within so many days of time, the time it takes me to perform the global coverage is going to depend on the size of my resolution cell. So if I just give a simple example, kind of schematic, if I have my specular track and I've gridded my Earth at 40 kilometers, so I'm assigning one observation to each one of these cells. I mean, that's not, of course, exact. I mean, this example, that's not really giving a good rating of what's going on in this cell. Let's just look at the coverage problem. I could maybe have some type of interpolation or something like that. So then if I increase my resolution, or now I have a 10-kilometer resolution, you obviously see it's going to take me longer to get the global coverage. So it's kind of a trade-off to resolution and the time it takes to get the coverage. Okay. Again, I wasn't going to have a lot of signals of opportunity. I was hoping to stick just with the GNSS-R. This is an example with Snoopy, which Roger is going to talk about next, where we looked at the global coverage, and this is based on a different altitudes of when we reach the maximum coverage and the revisit time versus cell size. Even though it says Snoopy, I'm looking at this reference. This reference was GNSS-R, so this may be relevant to, certainly the basic principle is relevant to both. So, yes, as I increase my cell size, of course, it's going to take a little less time to get my global coverage, less time between revisits. Okay. We talked about some properties of the signal. We talked about things being coherent or specular and diffuse scattering. Now let's get a little distinction and understand what's not necessarily a binary distinction. We can talk about variations of incoherence. So let's look at another way of thinking about this difference between specular and diffuse scattering. So let's look at the signal that's at my receiver and what's coming in the front end, and I'm doing my correlation, and I'm getting one sample of my delayed Doppler at a given delay in Doppler. So let's say we want to pick the delay number at the specular point, just as an example. So I'm getting a single measurement correlating with a local copy of the code at a given delay, a given dollar. When general, that's going to be a complex quantity. If I would plot that in the complex plane, my first sample of my delayed opera map at some given delay will give me this vector in the complex plane. Okay? Now, I'm going to now calculate the DEM I plotted, so I'm going to take the magnitude of this vector, magnitude squared, and I'm going to get a number. Okay, so now the question comes, how do I combine that with the subsequent measurements of that DEM? So let's say I'm going to add together the complex quantities. So in these two examples, I have the same, the set of vectors has the same magnitude, but notice in this example, the variation of the phase between them is relatively small. So if I add together all of these vectors in the complex plane and take the magnitude, I'm going to get this red vector. So I'm going to get a large magnitude for that. So corresponding to the noise, I'm going to be able to increase my signal to noise ratio by adding together these complex measurements of the DEM. Okay, what if I look at this example? And when I drew this, these four vectors I show here, I kind of assume, four all had the same magnitude, but now I'm adding them together with different phases, widely different phases, randomly distributed phases. And if I look at adding them factorially, adding the complex quantity together, I get this very small vector. So that says I'm really not increasing my signal to noise ratio. But this is another way of thinking about the difference between coherent and incoherent signals. In this case, I can assign a single phase to what's coming out of my DDM. Basically, as I'm moving in my orbit and I have my rough surface, that phase is changing smoothly. Well, in this case, a non-coherent case, I'm seeing a reflection from any points of the surface of the Earth. So any small change in my position is going to add all those points on the Earth together with slightly different phases. So the net phase is going to be pretty much random. So that's another way to think about the difference of coherent and non-coherent. And also with coherent, I can track this phase and I can estimate the path delay based on phase, which I can do very accurately. Okay, so this gives me one idea of doing a test for a measured signal, is it coherent or not? So one test would be, if I take my signal and then I just change my integration time, which amounts to averaging together these complex correlations, versus calculating the magnitude and then just averaging together the magnitude, which I might call non-coherent integration. So I do my coherent integration, and I do two different integration times, and if my change in my power is proportional to the ratio of those two integration times, then that's going to tell me that I'm coherent. So I can take this and convert it into a test where I can set a threshold on this ratio, and if it's above this threshold, then I said, okay, I can put it into the category of being coherent. Okay, now this isn't always practical with operational data, but this needs me to be able to vary this integration time. Usually that's a fixed quantity in the receiver because the raw data is my supply bandwidth. I certainly can take snapshots of that raw data, download and process it, but I can't do that operationally. I just need to pick an integration time and look at that. Okay. The other test for incoherence is we kind of showed this before, we showed an example like this before. Why have a coherent signal? The power of the DDM is going to be confined to a pretty small area because the power is coming only along one delay, and any spreading we see here is just the effect of basically convolving with the ambiguity function. But here with the diffuse, I have more power spread out over more delays. So I can come up with some metric based on how much power is within some box versus how much is out. So I can vary these numbers, but basically I can have the power inside a box. Takes a signal to pick three delays and 5 Dopplers versus the amount that's out, which is everything outside of the box, and we can apply this at the level 0 or level 1 data, which is a standard data product that comes after the integration. Okay, so this is another test. And then we also test the similarity of the shape of the DEM to a pure ambiguity function, which is basically a little more sophisticated than here. Instead of just counting how much power is inside and outside this box, we actually look at the shape of this function. So this is kind of another way of looking at how similar my DEM is to the shape of the ambiguity function. Okay, so this shows some examples of the measurements that they made. So the brighter colors, the red is more coherent. So this is this polarization power ratio. So that is this value. So the higher this number is, the more powers in the small range of the late opera bins. So this kind of shows, what you expect. These are all, wet areas, river areas. I'm actually, working on a new project with an ecologist at Purdue who's interested in the flooding in Bangladesh, and the reason I think we can get good measurements is that's all very wetland areas, very smooth water surfaces, so that's all highly coherent. Some of the rivers in the Amazon, Everglades are all very flat water surfaces to give good coherent measurement. So here we apply the threshold to these values, and we say, is it coherent or not? Okay. All right, so the other people by the same authors, this is a group at Ohio State University. They looked at the electromagnetic modeling of this, kind of what it what the range of roughnesses or ocean winds that would get reasonably to be coherent, so to get an idea of kind of how much of the world is going to give coherent reflections. So an L-band with GNSS uses is really only up to about 3 meters per second, which isn't a really high wind speed that we can assume the surface to be coherent. We go to P-band, and again, Roger's going to talk about signal to opportunity. I'm just putting as an example. We get up to about 7 meters per second, which I think is around the median wind speed of the global ocean. So 50% of the ocean would be coherent at P-band. We believe, basically, models. Similarly for land, about 7 centimeters, which doesn't cover a lot, like an agricultural land would be able to run smaller than 7 centimeters. This gives a good belief that L-band from Cygnus is going to be coherent over many land surfaces. And some of the soil moisture retrievals that are done assume coherence data, which is good. So get the higher resolution with the smaller soil. At P-band, we believe up to 30 centimeters, which is a large amount of the Earth's land surface. Okay. All right, so any questions so far? Let's see how we're doing. Oh, I'm at 2 o'clock. I think I'm running a little bit over my schedule. Okay, nobody tried to stop me, so I'll try to finish up. We started a little bit late. Okay, GNSS-R observables. Now, we looked at the basic measurement. Now we'll look at some of the things we can do with this data. Let's, and I think as an example, let me just see where I'm at. Okay, so I didn't get down the geophysical retrievals because I wanted to just talk about observables. So I'm going to kind of talk mostly what's done with Cygnus and put it in the context of remote sensing levels. They talk about remote sensing data. They usually talk about these 4 levels, maybe 5 levels in different levels of processing. So the level 0 is what's coming out of the instrument, and that for most users that's not that useful. Sometimes that's not even complete. The level 1 is you've taken the output of the instrument and converted it to measurements that are in some traceable, standardized unit. So that would be, for my delayed opera map, that would be units of power, either watt, I think you could also, because it's an integration time, put it in terms of energy, it's usually in terms of watts. So that's still, the calibration we've done is to convert, this measurement that's in some arbitrary digital count to a measurement that's in physically meaningful units. Now, there's a number of steps to then take that to the geophysical quantity we're trying to retrieve, because this measurement still involves all of the parts of the measurement, all the things in the instrument that are other effects other than the geophysical retrieval. So we still need to look at the relationship between that output of the instrument in watts and something related to the geophysics. So earlier I talked about this calibration in terms of using the noise load, or in terms of antenna swapping, that basically goes from digital counts, which would be the level 0 product, to a one-to-one mapping between digital counts and the instrument output, the DDN, units of power. Power versus delay and volume. Okay? But now to remove all the parts of the instrument, all the parts of the measurement, so that we get something that is related to what's going on the Earth, we want to pull out this bistatic radar cross section. So if I go back earlier and I have my radar equation that, remember, had this integral over the surface, but I say that within a given delay and Doppler, I'm going to assume a lot of that geometry is the same, and I'm going to do just the integration over that area that the ambiguity function is not zero, is not small, and I invert it, and we can go through this inversion of the radar equation where I have the received power at in level 1A product. It's been converted to units of watts. I have my path loss here, so I get my orbit of my receiver, my orbit of my transmitter, calculate those ranges, I get that, right? I have any other losses of modeling, atmospheric losses, anything like that. Those typically aren't big. I have my gain patterns. So I need to know a model for the gain of my receiver and the gain of the transmitter, which can become complicated since I'm using a non-cooperative transmitter, right? So I need to somehow model that or extract that information somehow. And then I have all my 4 pi's, the path loss and the effective area, the isotropic antenna here. Put all that together, that gives me the inversion of the radar equation, a scattering cross section as measured at a given delay and Doppler. Okay, so now I'm making my measurement based upon a segment of the delay Doppler map in terms of N delay and NF Dopplers. So I basically just average this, but I want to weight the average by an effective area. And this effective area is a way of approximating the shape of the ambiguity function, because it doesn't weight all the delays and Dopplers equally. Okay, so all this comes together, and I get an estimate of my normalized bistatic radar cross section. And then, and then this normalized bistatic radar cross section is then what, again, I relate to geophysical quantities, like wind speed, ocean roughness, whatever. That relationship between the electromagnetic quantity, scattering cross section, and geophysical quantities is usually called a model function of geophysical modeling. I'll say a few points about the levels. Level 1 and level 1A, level 1B. There's some differences in how different groups define it, but I think the important thing here is that level 1A is still in units of some physically meaningful units, watts. All of these system level calibrations have not yet been removed. In level 1B, we remove all the system calibration, and I get something that is a measurement of a feature on the surface. But the important thing is, this is still a one-to-one correspondence between these two, right? When I go from scattering cross-section to normalized bistatic scattering cross-section here, I no longer can invert that and get to the raw data. I have to group multiple measurements together to a single quantity. That's usually what says a level 2 data quantity. And then I take this and get a wind speed out of it. That's also a level 2 data quantity. So it's a geophysical quantity, but I've combined multiple measurements and auxiliary data together, and I can't easily invert it. So that makes it a level 2 data quantity. Okay. Same thing I can do with the specular reflection. This is basically no longer a radar equation. It's sort of this freeze equation for communications. And the last thing I wanted to a little bit ahead of schedule, a little bit behind schedule, is kind of conclude with why is this useful versus other remote sensing measurements, and also why did GNSS signals, why would they really the first signals considered for signals of opportunity? And of course, implicit in that is what can we do with other signals? So let's first talk about why we should look at reflectometry. The advantages is we're making active measurements with free signals. We don't need to provide our illumination. So we have the high signal to noise ratio of an active measurement with the the use of a passive instrument. So we kind of combine the advantage of active and passive. We have the direct signal for calibration. We can remove some aspects of calibration, but we also bring in a lot more. We have the complexity of knowing what the direct signal transmitted antenna pattern is and things like that. We use forward scatter, higher signal to noise ratio, and we can make measurements at frequencies that are not protected. We are not limited to the few bands of microwave frequencies that are protected for science. So we can make measurements within the middle of bands allocated for communication, which are occupied by a very powerful communications transmitter. That's probably why I think that's really one of the best advantages. The disadvantage is, okay, we don't have a lot of control over where the signals are. So we have non-uniform, non-repeated repetitive sampling. Possibly this could be an advantage because this may break some issue with aliasing and stuff like that. I don't know. We are dependent on someone else's signals, right? We need some additional calibration, such as the antenna pattern, the orbit, all that. And of course, some of these communications systems are very complex. They may be switching between spot beams. They may be dynamically allocating channels, and we need a way of being robust in all of that, which is, may not always be easy. Okay. Lastly, why GNSS? Why all of the signals that are being transmitted, why are navigation signals considered first? Well, the real reason is I began my career at GNSS. My PhD was related to navigation. I was not involved in remote sensing at the time, so for my story, that's how I got into it. It didn't come from remote sensing. It didn't come from communication. It came from navigation. Okay, GNSS orbits provide global coverage, continuous global coverage of the poles, equator, with minimal force satellites visible everywhere. L-band penetrates the soil to about 5 centimeters, which could be a limit, and they're also not sensitive to some features of the ocean because the ocean has features that are smaller scale than the GNSS wave. Okay? Important, we have this pseudo-random noise code. We can generate the code inside our receiver to perform the delayed or mapping, generate the ambiguity function. That is a big advantage. All right, so now my part's over. Second part, Rashmi's going to talk about what we can do with other signals that are not GNSS. All right, thank you very much. Any questions? Yeah. $34, $74. Okay, I'm sorry, I don't know, like, get microphone on? Right. Okay, well, I mean, yeah, so, I mean, you know, I mean, ideally, this should be, I mean, if I have a perfectly coherent signal, this should be, linear, right? So this should be a one-to-one. So, you know, so the highest value, I guess, should be, well, it depends on the ratio of these. So the highest value should be related to the integration time divided by 1 millisecond. So if I do two values, you know, 1 millisecond, 5 milliseconds, you know, my perfectly coherent signal, that would be 5, right? So you're saying kind of, well, where do we set the threshold between those two? You know, I think it's, you know, more like an empirical, you know, where we set the value, but you know, you calculate what the theoretical value should be for a coherent signal. It should be such that, you know, this ratio is you know, equal to the ratio of the integration times. But we don't have like an equation or anything to actually calculate what that is, but you'll know what the upper end is by you know, it being linear. Okay? Okay, I think now we want to go on a break, right?
Thank you, Dr. Harrison. Now we have third session on SOOP reflectometry by Rashmi Shah. Now I invite Dr. Rashmi Shah to please come forward. The final technical session of the day, SOOP reflectometry and its applications, delivered by Dr. Rashmi Shah.
All right. Good afternoon, everyone. Rashmi Shah. In addition with to being the supervisor for the system and message and promotion laboratory, I'm also the instrumentation and future technologies chair, technical committee at the Geoscience and Remote Sensing Society. That's the committee that's actually sponsoring this event. So it's under that role is why I'm here. Okay, so a little bit about myself. I have a little bit of a mountain to sea kind of story, and that's sort of what I do. I do both land and ocean remote sensing. I grew up in Nepal, moved to high school in Florida, so you know, going from a place with no ocean to a place with no ocean. And then went to Rochester, New York, where I saw a lot of snow again for undergrad. Then I did my graduate work with investigators here, so former students. And it was Lafayette, and then I've been in Pasadena and GPL since 2014. Where I've been working on mainly signals of opportunity, which is technology development for land and bush. I've done some other stuff at JPL as well, so if you can talk to me, talk about the other stuff. Um, So what I'm going to touch a little bit about SOAR concept. I think Jim was, Professor Gators is going to cover a lot of that stuff, but I'm just going to expand it to different frequencies, so some examples. And then talk about stow and slow motion sensing using the signals of opportunity. And these are signals other than GNSS that I'm focusing on in terms of the reflectometry. But I'm also going to touch on a concept called SOAPs on the amateur radar, and then show a little bit of results from motion remote sensing using remotes. Where is Okay, so something about electromagnetic spectrum. You know, we have something like 30 to 30 megahertz that's used for communication navigation. These are the signals that are, you know, anything here, like our radio signals, as well as our cell phone navigation, but also our TV signals and any kind of frequency. We have this frequency that's available to us, right? Between that, there's some that are allocated for science purposes. These are where your radars, radiometers, and if you read and there's some that's allocated for Earth to ground communication and navigation. That's shown in these yellow signals right here. And what you see is these frequencies are a little bit complementary to the signals frequencies that are allocated for science purposes, right? That's new. So what essentially means is if we figure out a way to use these signals, we're expanding the frequencies of areas that we can do science with. And different frequencies react to the surfaces or the atmosphere a bit differently, so you can understand about Earth a little bit differently. And that's the big motivation for us to do this, is expanding our available signal frequencies that we could do that. There's some frequencies that you would have no way to access otherwise. If you look at the low frequencies over here, you know, there's no application for science in this area, right? So that's another area that we're focusing quite a bit. Is this P-band, or what's called UHF band, and we use those for a lot of land sensing purposes. Yeah, keep going. So what do we do? For GNSS-R, there's locally generated, you know the PRM codes, you can generate them and use those as a reference signal and do your correlation and do all everything. But for a lot of communication signals, you don't know the signal that's being transmitted. That's actually their noise. What you want to know is that they're as close to noise as possible, and then you use the direct signal as a reference. So you always have a signal that's you're looking at direct, that's your reference, and then reflection from the surface that you're of interest, and then you do cross correlation and do the same kind of processing. A lot of the principles that were shown by Professor Garrison that becomes useful. The reason why you can do this with communication signals, even with the small antennas, are because communication signals tend to be transmitted at higher power because they're used for communication purposes. The air rate has to be low. They're transmitted at higher power, so you take advantage of that and use it as a direct signal. So it's essentially, these non-science signal that we're using for science purposes. Advantages, some of the advantages are they operate at any frequencies where a transmitter exists. So again, as I touched on that earlier, you have a strong coherent transmitted signal. These are high powers. You have active sensing, so it's essentially an iSky radar. That where your transmitter is something else. You're looking at forward scatter, which for a lot of surfaces that gives you higher SNR because, and Professor Garrison already touched on it, a lot of signal gets reflected in the forward direction. And your resolution is either set by signal bandwidth or transmitting signal frequency. And I'm going to touch on how you can improve about that resolution a little bit better too. And then your observation is either time or power. So some examples. Just keep it doesn't look like the animation come through. Go back. So I'm going to talk about VHF, UHF, which is used for this. As a satellite communication, use of those signals for snow and soil moisture. GNSS-R is L-band right here, and I'm also going to talk about KU band and K-band, which is used for TV, satellite TV in the U.S. And we've used that for sea level measurements. I'm going to talk those two application sides. So with that, let's get into the how are we getting all of these. I'm not going to touch about the ocean surface currents, but you can actually do that with Doppler signatures. If you're looking at it, and there's a paper on river currents based on that, which I'm not touching about it, but I do want to mention it. But we get snow information, which is snow water equivalent. That's the amount of water that's in the snow. So it's like snow level times density. Uptake is obtained by phase of things. We get root zone soil moisture, which is the soil moisture in the top meter of the soil, or up to the top 1 meter of the soil by looking at the reflectivity of the signal. And then ocean height, also looking at the path delay. So we have 3 different observable and 3 different applications I'll touch upon. So, okay. So as I said, what you really get is when the signal gets transmitted to different surfaces, you get either a coherent reflection or a incoherent field. If the frequency is low, the lower frequency, that is wavelength is higher, you tend to get a little bit more coherent signal, or they don't scatter as easily, and you will get a lot more coherent reflection, especially in the area of snow. And even in vegetation, we have seen that we tend to get a little bit more coherent signal when the frequency is lower. And we look at that for snow measurement, the coherent reflection. The incoherent field, you can't actually look at it for vegetation, although I'm not going to touch upon it. But essentially, the observable that we have is we cross-correlate the direct signal with any reflection we see, and we get the waveforms. It's going to be delayed out of that once we start moving your receiver, but when you're looking at a tower, and a lot of these transmitters tend to be geostationary or geosynchronous, so they're not moving too much. We don't have a lot of Dopplers. You can just cross-correlate and delay the wave if you're in the tower and get the waveform, and that's how looking at the shape of the waveform is only going to do this. So, in terms of soil moisture and snow, what happens is when your signal gets transmitted through a snow medium, it'll change the angle of refraction a little bit and cause a little bit more delay in your signal, which will also show up in your phase of your signal, that a little bit of delay in the phase change. And that phase change is what we use to see how much speed has changed or snow water equivalent has changed. So that's how we get the information about snow water equivalent. And it's dependent on the frequency of interest. And then the reflectivity, when it goes through completely, we will see reflection from the ground, and then reflectivity will also give you soil moisture. And actually, depending on the frequencies you're looking at, you can actually do both of observation at the same time as well. So for P-band or for 260 megahertz is what we used for some of the information. The phase change happens. The 360-degree phase change happens at a speed of about 606 millimeters. That's actually quite a bit of snow in there because snow density is about 0.3. So when 60 centimeter times 3 is how deep the snow has to be for you to see fade 360 degree phase change. So it doesn't happen as much. Now, so you get a lot of sensitivity, or not sensitivity. You get your phase graphing doesn't happen as often. So if you're observing things, it has to snow a lot before you see 360-degree change. So you can actually measure that change over time quite easily. And these little ripple that you see is caused by multiple reflection that happens internally in the snow structure. So now what happens if you observe it at different frequencies, right? GNSS-R, the same thing will be at 50 or 75, I think it's about 75 millimeter of sweep. So your phase will wrap quicker. So if you're observing your phase in your snow measurement and observing in a few days and a big snowstorm has happened, you will miss that because your phase will have wrapped. So that's another motivation of why I wanted to go to PLAB to do this. We also did a lot of sensitivity tests to see what happens at snow grain size, snow density, how do things get impacted by those two. And we saw that we did, snow grain size as well as snow density. The base doesn't get impacted as much by those two. Then we did one more simulation. How many of you have ever seen snowpacks? Anybody? All right. What happens is if you imagine snow will go, it's like a cake. Your different layers of cake will show different layers of snow storms, right? A snowstorm will come and then it will melt a little bit, but then there's really nice formation and then more snowstorm will come. So it's kind of like different layers of cake that we can think of. And so how does that impact your thing? If it's not homogeneous snow, but it's different kind of snow, which is called stratigraphy. So we did some simulation for that based on real data of snow measurements, and then how the snow behaves at different, like how sweet will be different. So your amount of your snow is denser at one layer and not as dense and then denser, and kind of do that. And so we looked at that in our measurement too. And notice that we don't see a lot of change, so that for multiple different frequencies here in that simulation, assuming that it's a single layer, assuming that it's a different layer, it's right on top of each other, so you don't actually see change. There's a little bit of change here, but few degrees of changes, but you don't see a lot of change either. So what this is essentially telling us is, by looking at the forward scatter phase of these measurements, we can actually get information about the snow water equivalent, which is the volume of water present in snow, which is really useful for water research purposes, right? Because all of this snow, like in case in this region, for example, when the Himalayas melt, you get that water for drinking water as later on. So you see that snow, water is available and how much is melting and turning into runoff. You can do those measurements with this technique. Now, the other thing that we need to know is how wet is the snow? Their snow does it have a lot of water crystals in it, or is it very solidly packed, solid snow? It's another thing that can impact, and that's called wet snow. So for us to understand what happens when the snow becomes so wet, from when we go from winter to spring, as the snow gets, more sun happens, snow starts melting, and there's more water content, and snow what happens. So for us to understand that, we look at the volumetric constant of snow, where we have the imaginary part and the real part. And if you keep going, and what we notice is when the snow is not as wet at some certain point, your reflection changes from closer to ground to closer to air. So when the snow keeps actually it should be this is soft. But as the snow gets more and more wet, your signal doesn't penetrate as much, and you start seeing reflection from closer to the ground. Because when there's more water content in any microwave signal, the microwave signal does not penetrate water as much. It penetrates snow very well, but it doesn't penetrate water. So if you go to the next. So all of a sudden, what we see is when it's dry snow, our phase is related to speed, and it's at a positive relationship. But when it's wet snow, the phase gets related to the snow depth. It bounces out from the top, the air starts dominating, and it bounces up from the top. And we also see a negative phase correlation with that. So it becomes a snow depth measurement instead of speed. So what we did was, this was all theory and simulation work that we did. And then we set up an experiment for PVAC, or for UHF frequencies, which was for both 240 to 270 megahertz as well as 360 to 380 megahertz, and try to retrieve speed from a tower experiment. So this is in Fraser, Colorado. They get a lot of snow. It's called icebox of the United States, lower 48. It's the coldest part, and they get a lot of snow. And we have our colleagues from Forest Services who actually did snow pit in situ measurements too, so it's a calibrated site. So we had information about the in situ measurements of speed, and then our retrieve suite, where we recorded the signal, cross-correlated, and then looked at the phase over time, over a couple of months. And we got a pretty good relationship, what we expected from theory. And the RMSE was about 7.5 millimeter, which was pretty good. So, we were able to verify this wind tower. And then we added to our site, and no vegetation, it was very inside, And then we wanted to understand the effect of vegetation as well, because a lot of snow usually is under canopy. And what happens when that happens? This is not the best picture, but what happens is you see a lot of it's not uniform snow anymore when the trees are so we're still advocating over a specific area, right? This is the Fresnel. You're expecting a point, and the Fresnel zone is your coverage that you're getting spatial resolution. And then within that, we still have some trees, and it's not uniform, but we still see the effect of the phase change, the same as we see from the uniform site here, the non-vegetated site. So what we found was at these frequencies, about 3 meters snow, 3 meter height of trees didn't really impact our signal as much, because the wavelength is about a meter. We're actually passing through the vegetation, and we can still see snow movement. And then we also looked at it from that period where I said it's going to be a negative correlation for snow depth. And we saw that negative correlation. And then in the summer, we have looked at the site for stone bush. So especially stone bushes. So we actually have stone bush sensor at various different depths. at 5 centimeter, at 10 centimeter, at 27 centimeter, and 40 centimeter. So we have that. And we looked at the effect of soil moisture change on our reflectivity measurements as well, and then try to get retrieve results of moisture out of these measurements. And we got about an RMSE of 0.024, which is pretty decent for the site that we were looking at. This site is not the best site for doing soil moisture experiments because it's pretty broad. As you can see, it doesn't get, every jump here is supposed to be a rating, and it doesn't get as much rating in the summer. So we only did this experiment for about a year and have stopped that. But we were able to see the sensitivity to changes in soil moisture from this measurements. And then Professor Garrison is actually a PI of this project called Snoopy, and it was mentioned earlier today. We proposed a mission, CubeSat mission, to validate the measurement from space of signal spectrum reflectometry concept. Professor Garrison is the PI, and it was a joint effort between Purdue, Goddard, and JPL, where the purpose was, let's put a satellite up to validate some of our measurements concepts and really try to understand the link budget, how can we, from the orbital altitude as the speeds are changing, as well as the RFI effect. Well, if you have a broad beam antenna, what is the RFI, radio frequency interference, and what is that going to be? And then also try to predict a delay and Doppler based on the orbits that we have from this non-cooperative transfer. So those were the purpose of it. The other thing that this Snoopy mission has is it has a single antenna that's looking at, that's recording a direct signal from the top. And it's an equal antenna. So one polarization of direct signal gets from the top, and the reflected signal goes from the same antenna. When it changes polarization, the antenna changes polarization on the other side. So we're capturing both of them from a single antenna rather than having two different antennas. And if you go to the next slide, and so again, did some simulation on trying to approximate how you can get retrieval out of it based on the SNR that you get from the two antennas. And it's the gain of the top antenna and the bottom antenna comes into the play in understanding your gain ratios to understand your connectivity measurements. There's some pictures of Snoopy integration and testing. As it was done, there's a satellite that's out. I think this is a vibration, but this was integrated into the dispenser, and this was operations. Keep going. This was launched. I didn't have the video. It's not open. But I had a video of it being deployed from ISS. And then, so this launched last March, and it was deployed in April of 2024. And then after initial initial communication and checkout, we did data recording of in two different modes. In the delayed output mode, we had a way of computing the delayed output mode while on board. We were to upload the delayed output prediction on board and record it, and then also record some raw data because we wanted to understand our environment as well as be able to process things down. So we have results from one of these signals, which is from June 6th, of raw signal, and it was collected over here at off the coast of Brazil. We saw some spectrum in the 260 to 262 megahertz. So this is 240 to 270 megahertz signal. We were able to see some spectrum and then we use that to compute our waveforms. I'm showing waveform, but we actually computed the waveform. This is corrected for the Doppler that we were predicting. And this is the direct waveform from multiple channels, and the reflected waveform from multiple channels. This is a reflection of our ocean. We were really hoping for data over land, but we were not successful. We got some reflection of our ocean. And Professor Garrison talked about the spreading that happens. So we see some of the spreading, a little bit of spreading in the waveforms, the reflected waveform, from these channels of our ocean. And they're all pretty close to each other when corrected for noise and stuff. So we have some consistencies, and this is very preliminary data. There's more analysis being done and being looked at. All right. The next thing is on synthetic aperture radar. So one of the things I've been working with some colleagues at JPL over the last 4 years have been how can we combine the SAR technology with signals of opportunity with some of the other stuff that's going on. So it's really the use of sparse array technology, which is use of multiple platform, kind of a distributed system observing, and combining signals from multiple different platforms to get higher resolution, SAR-like resolution. So it's not just these line resonance that we get from reflectivity, but rather swath resonance that we can then use for resonance. So that's what SOAP-SAR is, and we've been really trying to do that for both SWE as well as results evolution. And how do you do that? So, you know, if our bandwidth of the signal is about 20 megahertz, your resolution, your first Fresnel, first resolution, not the Fresnel zone, but the bandwidth resolution comes up to about 10 kilometers. But if we try to have multiple different receivers that's looking at the same region, what you get an offset in space a little bit. What you see is you can focus on one area because your second area, which is your ambiguity area, is going to be different, and you can kind of bring that down a little bit. So you kind of do a little bit of focus processing from multiple receivers in a relay that's flying in a row or something, and use that to really improve upon your range compression, as well as Doppler, and then do some Doppler processing to improve your Doppler resolution. So you improve your delay resolution by doing a multiple receivers, and your Doppler resolution by doing you're reducing your time integration time, and with that, what you can get is you can get a focus resonance at various different points. You can do that over at each point to kind of to processing, and you can improve your resolution and do a get a SAR-like resonance from signals of opportunity. So to show that, now to get a Doppler, you need to have a moving transmitter and a moving receiver. We didn't have a moving transmitter. Well, a transmitter moves a little bit, but not too much. It's a geosynchronous transmitter. So we put it on an aircraft and did some flight campaign to see if we can get some resonance there from one receiver. And I'll show you how we actually did multiple receiver simulation for one receiver. And we did some experiment to see if we could get a SAR-like image from this technique. So we flew some engineering experiment as well as some science experiments in 2023 to do that. So next slide. And remember when I introduced this concept, I said you need multiple receivers to do that binary thing. Instead of, and with airplanes, you couldn't have multiple airplanes flying. So what we really did was we flew one airplane in this track, racetrack like platform, race like pattern. But each time we were flying a little bit separated. So we were trying to aim for 10-meter separation each time that we were flying, and then use that to simulate multiple receivers concept. Now, you can do this over land. You couldn't quite do this over ocean because the land doesn't change too much over the 2 hours that they did our resonant twin. So we could actually say, that this was, even though it was done at a different time, we can still kind of process it coherently together. We, if anybody has done flying, it's quite hard to fly around 10 meters, but the pilots were able to do that by assuming that they were coming into land and they're running at the same time. So just one thing is we had to really think about how could we fly consistently and coming back every 10 meters. And then in the end, they did 11 tracks with 10 meters spacing published. Then the way we did that, processed this data, was we then took all of that data, corrected it for the position of our aircraft, as well as the geosatellite position, looked at it all, and did a match filter processing in a 10-meter by 5-meter grid. And there is a paper where you can actually go and work through the math and how we did the match filter processing. And process it to get SAR-like image over that 110-meter distance that I showed you earlier. So go to the next slide. And we did that for all the period of data that we collected. So if you look at this data between in August, February, and March, 3 different times. In August, this image is the same, but because I don't have an image, this is just a Google image. But this is a no snow image. There was snow in this thing, and between here and here, there were 2 big storms. There was more snow in March. So between the 3 times, what we saw consistency in the reflectivity results that we see. The patterns are very similar now. So Indian version as well. So it showed consistent spatial patterns over multiple different time frames, which really told us that yes, we could possibly use this as a SAR processing to do SAR kind of measurements. Go to the next one. And then we zoomed in into a couple of places. One was over water area. So you can see that it follows the pattern a little bit. There's a little bit out here where it's more power, so red more power and blue's less power. So from the water bodies, we would expect more power. We see a little bit difference from the image satellite, which is right there. And that's because if the soil is really moist, we would also see high activity. So we think this area was just really moist, but we were able to see a little bit of coastline change from this measurement, which was a good way of saying that we can process this at a finer resolution. I think the next one is figures more compelling. So go to the next one. Oh, okay. Apparently, I may have deleted one slide here. But then, if you go back one. So, I think you can kind of see it right here if you really zoom in. Is we have a forest here. When we zoomed into the forest, you can see it more defined, that it follows the forest line a little bit more. At very, very fine resolution. So what we are saying that we can actually see the differences between the forest and non-forest. There's a little bit of attenuation that happens with the forest. We expect a little bit lower power, and we were able to see that at the forest line. So that actually really gave us more confidence that yes, we can do satellite measurements and get the satellite resolution with the technique like this. The experiment that we did was not as, the antenna gain was not as much as we wanted. We didn't get full retrieval out of it, but we were able to show that this engineering measurement this actually works. Now, next thing is on the ocean front. We've been looking at path delays. It's very similar to phase measurement, but instead we're looking at the delay side and trying to get altimetrics or sea level height measurements from the signals of opportunity measurement. And if you remember when I showed the spectrum very early on for a KU K-band, we have around the world just different transmitters, but there are many transmitters out there that are like 400 to 500 megahertz wide bandwidth signals that are used for direct broadcast services. So when you're looking at using those signals, and the reason why the bandwidth matters is our accuracy in the height is inversely proportional to the bandwidth of the signal. So more bandwidth will give us better accuracy in our altimetric signal. And it's also SNR limited, but that's the relationship that we've been playing with and trying to get high resolution or high accuracy sea level measurements from these signals. So we looked at a signal called direct TV, which is a satellite TV in the US. And the bandwidth is about 500 megahertz in dense experiments. So next one. But before I go back. So but before I show you the KU band signal, our colleagues in Spain actually did some X-band experiment at 11 gigahertz and looked at similarly to other digital satellite TV signals and got an observable with a precision of about 10 centimeters for a wind speed of 3 meters per second. So they did a little bit more statistical analysis on this noise. So if you're interested in that, I encourage you to go look at this. And what we did was we had, again, two antennas, one that's down. This is off the coast of California, and it one platform that's still over there. We did look at the full 400 and 500 megahertz signal in both KU band and P band. And again, this was a good site because it was a calibration site for altimetry satellites. There's that US has been flying with GNSS for the last 30 years. It was a well-instrumented site that we put our instrument on. So we have a lot of real, in situ methods there as well. So we compared our measurement with the in situ measurement. We had RFC of about 3 centimeters, which was pretty good. And again, if you expand that same relationship and see what we can get it from space measurements, where we can correct for, again, position has to be corrected for other things, you get about 4 to 6 centimeters from space. So this is another way of getting sea level height measurements by not putting active transmitters on, but you can use the same technique for sea level height measurements. And you get pretty decent coverage over the world. At some point, I did a coverage analysis to really look at what kind of coverage are we going to get. And this is about a day of coverage from 8 satellites. You get pretty decent coverage across the world, around the coast region, because people don't live in the middle of the ocean. You don't have transmitters in the middle of the ocean. But that has changed. This is an old analysis. Things have changed since then, so there may be more transmitters that we actually do in the middle of the ocean. But coastal altimetry is very important as the sea level is rising. Coastal altimetry, that's the application that we're targeting. And motivation behind it has been twofold. I said coastal altimetry for people, but for science purposes, there's also little eddies that the resolution, that current simulation that we have, we don't have as much observation in there, so it doesn't help. We don't see as much detail about this ocean structure. And then if we put more data, we will see better structure of our coastal eddies. So that's another reason why we would want to do it. And why would we care about that, right? But the things that we care about it is for storm surge prediction, for realistic wave model development, as well as some scale processes that can be very, very temporally dynamic. So by putting low cost receivers, constellation that we can get with temporal resolution, and you can get the information about it. There is a mission called SWAT that's doing high resolution or spatial resolution measurements of these eddies, but the temporal resolution of that is about 20 millions. And you don't get, the things change quite a bit on there. So this helps with the temporal resolution again. And, you know, this was the coverage that we showed, that every day you can get pretty dense coverage, so you can get more information on it. All right. I think it was, you know, a summary slide, but essentially, I think both Professor Garrison and my talk has really talked about how can we, what the reflectometry really is. It's really a third way of sensing, right? It's a good combination of active and passive, because it's an active sensing and passive level. You can use that has been done significantly with GNSS-R. So we're expanding it to different frequencies. Started about 15 years ago, and we've been looking at many different frequencies, but it is a pretty recent area of research, and there's a lot that can potentially be done. Okay, that's, thank you. Questions? Yes.
Thanks a lot, you and James. It was wonderful, and I guess many of us found it was very interesting also. Earlier I have worked with altimetry data, which is also very limited to use if you see about image remote sensing, compare image remote sensing altimetries. Very few people work on altimetry. Similar this particular signal opportunity is really fantastic. A few days back, I have tried to do analysis on data, again that's a signals data, so I was able to do some analysis. So that's fine, but this should be on other data sets. So those are also very much interesting, specifically for me. So is there any kind of sample data or any other data sets or any other standard capacity of analyzing those data? So if you can share some of those sources, that would be very much helpful to go ahead and state. Yeah.
So I can touch a little bit on the Sloopy data. Sloopy was, NASA gives all of their science mission data. That's what the US data. Sloopy is a tech demo mission, and we have very limited data sets that the team is still analyzing. And Jim is the person to talk to at some point. he might be able to share the data in the future. For that, we have, as I said, as I showed, we had 5 or 6 data sets. Last year, solar activity in this cycle has been very, very active. And because of solar activity and it being a CubeSat, we lost the signal, we lost the satellite much sooner than we expected. So we don't have as much data. And the team is still analyzing it, and at some point, I think there is plan to release the data. Yeah.
Is there any other data sets? Not on the Sloopy, but there is another.
There's a lot of tower data sets. Some of the tower data sets we have, we have put it in some places, I think we're keeping that.
Yep.
And then there is way, Ravindra and I have been talking about what are some of the ways we can set up some test beds here to be able to see if we can get some more data.
Yes. Thanks a lot.
Thank you.
Thanks, actually. I had a question regarding the SOP, SOP-R. So, actually, this is nice talk, actually. And you did this experiment. I had just curious about the image formation. Normally, you have shown the track of the ground track of the airborne camera. But normally, in XR, we have actually the track of the SP points, which is not like a straight way. So how do you form this figure? And then the kind of Doppler also you have to use for the image formation.
So yes, we did correct for Doppler, and because this is a geosynchronous, that we oriented it in the direction so the circular point was straight as well.
So this is mainly for feedback.
This
Okay.
was for
That
Now you could use, think of it in different delay and Doppler domain, and that puts different spaces on Earth. And then you could kind of do focus processing for a certain area and try to remove the other ambiguity and do something similar for GNSS as well if you have a receiver that's collecting multiple things. So we've been working on some of those relations.
So this experiment is mostly offered to the geostationary platform. Otherwise, if your transmitter also moving, your receiver is also moving, so this kind of image formation would be very challenging.
Yes, it adds another layer
Yeah.
of correction that we have to do, but I think it is possible.
Hello, ma'am. I'm actually working on a PhD student. So for my thesis, I'm working on GNSS-R actually for snowden estimation. And we have set up a station, India's first station actually in Spiti Valley. And currently we are collecting data. So I want to know more about how I can analyze data with GNSS-R as well. Because we are currently estimating snowden. And we also plan to expand to snowboarding with it. So is there any studies or actually like where snowden is being estimated in the world using GNSS-R? So we can also process our data.
So how tall is your tower?
It's 3.2 meters.
Yeah, so I think if you go lower, then you have to do GNSS-R processing, right? And then tomorrow morning, Philippe's going to talk a lot more about it. But the way to validate it would not be with GNSS-R. In my opinion, it would be with any kind of in-situ measurements.
Yes, ma'am. We have a camera and we also have an ultrasonic snow sensor setup. Okay. And is there any study GNSS-R regarding snowden? So we can probably I think the coverage would be large, but is there any data there or something?
I don't think so. But let's talk a little bit about it. Any more questions? No, then thank you.
Now,
about today's event. Thank you all for coming. I feel that it is valid, informative to you all today. See you all tomorrow. And we have arranged refreshments for you, so kindly take and we have arranged photo session, photo booth. So if you are interested, you can have photos there. Feel free to access this photo booth. Yeah. Thank you all. Thank you so much. See you all tomorrow. Thank you.